Hello, and welcome to this Kistler webinar. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's session. Just to the right of the main presentation window is the Speaker Bio window, with background information on today's presenters. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed into the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenters, Robert Hillinger and Jim Macy. Robert Hillinger has a degree in electrical engineering from the HDL Modeling in Austria. Since his studies, he has worked as an electrical engineer, product manager, and business manager in the automation industry. In 2018, he joined Kistler Instrumente in Winterthur, Switzerland, who is a leading measurement company with their own R&D, production, and global presence. Robert Hillinger works as a business development manager and supports semiconductor customers to get better process visibility with dynamic measurement technology. Jim Macy has a degree in mechanical engineering from the State University of New York at Buffalo. He has worked in several positions, including applications engineer, regional manager, account development, and senior manufacturing specialist, mostly working within the automotive. In 1985, he joined Kistler Instrument Corporation in Amherst, New York, a leading measurement company with its own R&D, production, facilities, and global presence. Jim Macy works as an application expert assisting semiconductor customers to improve manufacturing performance and traceability with innovative dynamic measurement technology. Guys, welcome to today's event. And with that, I will pass things along to you to get started.
Thank you. Also, we'd like to also thank everyone here in attendance today for taking time out of your schedules. Robert and I are very excited to share this presentation on dynamic force measurement with piezoelectric sensors. We are convinced that all semiconductor equipment companies, as well as semiconductor manufacturers, will continue to benefit. Sensing force is a critical physical value in many production processes, especially when it comes to advanced packaging. As not everyone may be aware, Kistler has been around since 1954, and we are the pioneer in utilizing piezoelectric quartz crystals as the sensor's transduction element. Today, we are the leading company of piezo-based sensing technology, and we continue in advancing our unique sensing solutions for our customers. Let us first explore why force is utilized. Chip testing of semiconductors, as well as process monitoring and control, are widely done via the utilization of target-based, optical, and motion-based position sensing technologies. I'd like to point out that with these conventional measuring methods, the mechanical stress generated is not detectable, yet it is equally important. The applied force is critical in front-end processes like lead stamping, wafer grinding, wafer polishing, wafer dicing, and others. The same is true for back-end processes like die attach, wire bonding, and advanced packaging. With these processes, force deviations can lead to quality issues, which I want to elaborate deeper on the next slide. We assist clients all over the world with dynamic force measurement, monitoring, and control. Direct point of contact sensing enables one to detect the visible and the invisible assembly and handling issues. It provides a means for enhancing traceability to the tooling and tracking the overall assembly machine's performance. On the next slide, we will look at increasing market demands for the quality in moving forward. We are facing new product requirements from technologies like 5G, artificial intelligence, and smart manufacturing, which require more powerful chips, ramping up the need for continued miniaturization combined with complex chip architectures and require more advanced packaging. Stricter traceability requirements from the automotive industry and autonomous vehicle standards require cost effectiveness. There is widespread agreement that increasing the number of inspection steps, obtaining more data from the analyzing equipment, and assessing product variables are needed. Now I will pass you along to my colleague, Robert Hillinger, who will share some of our global application insight.
Thanks, Jim. Let's take a look at applications in order to illustrate the adoption of force measurement, starting from wafer fabrication, wafer level packaging, assembly and packaging, until testing. There are many process steps where you can benefit from applying force measurement, as you will see during the next few minutes. In the middle of the circle you can see the applications which we serve with dynamic force measurement today. Firstly, I would like to ask you to imagine the wafer manufacturing process, where the wafers are exposed to mechanical loads caused by polishing, grinding, sewing, manual handling, and many others. Keeping mechanical stress within the limits improves process safety. The introduction of thinner wafers have increased wafer sensitivity to mechanical loads even more and reinforced the requirements for monitoring and reducing mechanical stress in order to avoid the breakage and defect rates accordingly. The same is true for the lamination and delamination process, where you can monitor the applied forces in order to make sure the dies are not getting damaged by too much force. Another application is lead stamping, where the applied force has a correlation to quality parameters. Pick and place, sealing and molding, sorting and testing are further applications. In all these applications, force measurement helps to address mechanical stress issues like warpage, parallelism, tool wear, material change behavior, and malfunction. Conventional metrology, like vision monitoring, is in many applications not enough to make issues visible. Bonding applications like wire bonding, flip chip, die attached, wafer-to-wafer bonding are applications served by Kistler for many years. On the next slide I will talk about thermocompression bonding in more detail. As you know, you have to control temperature, force and Z-axis travel during the bonding process. The die is picked up by the bond head, held securely and flat on the bond head with vacuum. After the die is aligned with the substrate, the bond head comes down and stops when the die touches the substrate. A constant force is then applied while the die is heated up quickly beyond the solidus temperature. As soon as the solder joint melts, the die is moved further down to ensure all solder joints are in contact. The die is held up in position, allowing the solder to reflow completely and to wet the bump pads and copper pillars. While the solder is still in the molten state, the bond head retracts upwards, controlling the solder joint height. The bond head then releases the vacuum holding the die and moves away as the solder joints have solidified. The major process parameters like temperature, force, and displacement are continuously monitored during the thermocompression bonding process. As you can see from the graph, force is absolutely critical in that process. Therefore, a force sensor is integrated into the bonder head in order to provide a real-time force signal to the controller. This allows to overcome the challenges during the process. Let's take a closer look at this at the next slide. The application here shows 3 sensors mounted into the bonder head, which allows to manage warpage and parallelism as well. The beauty of the piezoelectric sensor is the high resolution, smaller than 0.1 gram, good repeatability and compactness, which allows to perform closed loop control at real time. The closed loop control shows here the controller such as PLC or industrial PC, servo amplifier and motor, and the force sensor and sensor amplifier from Kistler. The amplifier, which allows cycle time below 1 millisecond, gives you an analog signal which is equal to the force applied. This allows high dynamic force measurement and control in thermocompression bonding. In that specific case, a customer had some challenges with mechanical stress during die bonding. In addition, the end customer from the automotive industry has asked for traceability per product. Therefore, a customized force sensor has been integrated into a die bonder vacuum pickup tool. Dimensions were very tight, as you can see from the comparison with the paper clip. The customer is now able to measure exactly the mechanical stress which is applied on the die per pick and place operation. As you can see from the graph, he is monitoring maximum and minimum force values applied to every die. So he has full traceability for every product produced. A further advantage is that he needs less time to start up his production. If he needs new material which behaves differently, he can adjust the equipment to the new situation quicker. Now let's have a look at more applications. If you recall what I spoke earlier, wafer manufacturing has several applications where they are exposed to mechanical stress. With force measurement, you can correlate this mechanical stress to quality parameters. This is one benefit to keep mechanical stress within the limits. The second one is precise loop control. Similar to the thermocompression application, you can use the force signal to perform precise loop control, and you can achieve great downforce precision. Another customer applications where we are able to support is lamination and delamination. Now let's move on to further applications. Lead frame stamping, die attach and wire bonding are traditional applications and are supported by Kistler for decades. However, here as well miniaturization and higher quality requirements are demanding better process control and dynamic force control can add value. The types of wire bonder, like thermocompression, thermosonic, and ultrasonic, can all be supported with piezo dynamic force measurement. Further, piezoelectric force sensors allow to measure a wire bonder dynamic force in real time. Typical low forces like 0 to 10 Newton are measured in milliseconds and grams and can reveal potentially damaging conditions like head bounce, vibration, and malfunction during operation. In addition, semiconductor equipment manufacturers can use the signal for accurate and precise complete loop control. Die sorting is the process of removing a die, package, or device from one carrier medium and placing them into another carrier. When you install a piezoelectric force sensor into the die ejector, you are able to monitor the amount of force which is applied during the removal process. Many what I have said about bonding applies to sintering as well. One important thing to be aware is that the high temperature in sintering favor the use of piezoelectric sensors as they have a high temperature resistance. The piezoelectric wide measurement range is a feature which can be applied at shear bond tester. You need only one sensor for a broad range from 0 to 10 kN. We spoke about thermocompression earlier. This concept can be applied to flip chip and other bonding technologies as well. Transfer and compression molding is where a casting material is forced into a mold. A pressure sensor installed allows to accurately measure and monitor the fluctuations in viscosity. Deviations are indications for defective products, such as wire deformations. Test contactors, sockets, serves as the interface between the test handler and the semiconductor device under test. By integrating piezoelectric force sensor, you can ensure test performance for every insertion. In summary, we can see that dynamic force measuring can add benefits and value to many semiconductor production processes. Let's conclude on the next slide. Production processes are becoming more complex. Therefore, improved methods for process monitoring and failure identifications are needed to maintain or improve the quality and yield. Dynamic force measurement is helping with monitoring and controlling of the critical physical value force. Now I would like to hand over to my colleague Jim Macy to talk about the dynamic force measurement technology and its capabilities.
Thank you. And moving forward, I am happy to introduce our piezoelectric technology and share additional insight. Upon mechanical force loading, the piezoelectric crystal generates an electric charge response in picocoulombs that is directly proportional to the applied force. Due to the extreme high rigidity of the crystal, the overall deflection is extremely low, and as a result, the force sensor is very linear. This high linearity extends across the sensor's measuring range, which is of several orders of magnitude. Our construction of the force sensor starts at the crystal level and proceeds with its precision cutting, then advanced packaging to ultimately produce a high-quality sensor. The next slide, we will look at the demonstration of unique resolution which impacts in an industrial force measurement. In this demonstration, An O-ring is placed on a piezoelectric sensor which features a measuring range of 10 kilonewtons, or that's a capacity of about 1 ton of force. On the right side, we view a graph plot of force versus time, and we see the initial load spike, which occurs when you place the O-ring on the sensor, followed by the weight of the O-ring, and then concluding with removing the O-ring. Here we observe that the piezoelectric sensor, with its overall tonnage capacity, easily measures the O-ring with a weight of about 1/3 of a gram, and that this very low force is detected with high resolution. This unique capacity of piezoelectric technology enables one to view small force deviations that are not visible or possible with another force measurement technology. For example, strain gauge load cells being utilized in such applications. Next, we will look at compact size and further discuss rigidity. High resolution and wide measurement range combined with compact sensor size are very desirable features of piezoelectric sensors. Furthermore, the high sensor rigidity, which means low overall deflection of the sensing crystal during measurement, allows for excellent dynamic force measurement performance. Sensor installation is important to maintain this high rigidity. Hence, we offer several force sensor options. We also provide application guidance and consulting. In the picture on the right, we view the force calibration setup of an older style wire bonder. The next topic I would like to have a closer look at is repeatability. Repeatability is understood as serial precision. For example, conformity between several measurements that are performed in sequence and under largely unchanged conditions. Repetitive measurements are often required in production processes, and the sensing technology is expected to keep up over millions of cycles. In this demonstration, a servo press setup repetitively applies and removes 29.1 grams of weight over an extensive time. Throughout this demonstration, a repeatability of plus minus 0.1 gram is measured for the customer. I'd like to point out, for good repeatability, piezoelectric measuring systems provide an advantage in their ability to quickly reset the signal conditioner before each and every measurement cycle. Potential measurement errors such as external temperature influences are thus excluded from the measurement. On the next slide, we will look at some examples of force measurement systems for manufacturing. The piezoelectric force sensor requires a signal conditioner known as a charge amplifier. In the top view, the PLC, or process controller, receives the force signal and makes the decision on good or bad cyclic processes. In the below view, the PLC delegates the good-bad decision to the Kistler monitor, whereby the process curve is analyzed at high clock speed and the process result is reported to the PLC, as well as can be exported for database traceability. We are coming toward the end of our presentation, as the next slide is key takeaways. So in conclusion, piezo force measurement technology is the technology to make the invisible impact on mechanical stress visible. With its high resolution, wide measurement range, it can help increase quality and decrease PPM failure rates. The piezoelectric technology is ideal for repetitive manufacturing processes because of its high rigidity, there is no wear, this results in long lifespan. And finally, you have full traceability, so you can use the data to improve your processes further. We are looking forward to hearing from you.
Thank you so much for that great presentation. And now let's get to the Q&A. We have some questions that have come in from the attendees, so we're going to move into answering those right now. If we don't get to your question, don't worry, we will have an answer for you following the webinar. Now for our first question. In which semiconductor manufacturing process is dynamic measurement from Kistler utilized? Guys?
Jim, let me take this question. We are supporting customers worldwide, front end, back end, and with testing applications. Applications which we supported so far are polishing, backgrinding, CMP, dicing, lamination, delamination, handling, lead frame stamping, die bonder, wire bonder, flip chip, wafer bonding, sintering, die sorting, sealing and molding, sorting and taping, and test handler. However, we are learning every day, every month about new applications where we can add value with dynamic force measurement to our customers' semiconductor processes.
Great, thanks for that. Okay, now for our next question. How do I start if I was to wish to apply force measurement for the first time?
Thank you. That's a great question. We recommend that it's best to start talking with the measurement solution supplier at the offset of the project, as this allows important details to be shared and a tailored solution arranged that meets your needs. In addition, Kistler offers a white paper entitled Using Piezoelectric Sensors to Measure Dynamic Force in Semiconductor Applications.
Great, thanks for that. Okay, moving on to our next question. What is the maximum accuracy that you can achieve with your sensors?
I'll take this one as well. Piezoelectric sensors have superior resolution and repeatability compared to other technologies. Unfortunately, there is no single answer when it comes to accuracy, as the entire measuring system, the application, the environmental conditions, as well as post-processing must all be looked at.
Great, thanks for that. Okay, next question. Does Kistler offer support worldwide?
Jim, let's answer this from Robert. Yes, Kistler supports customers worldwide. Kistler has a worldwide footprint with local engineers in Europe, North America, and Asia who understand the semiconductor industry requirements and help customers locally to apply dynamic force measurement.
Excellent, thank you for that. Okay, now for our last question. How do you support customers?
Robert, let me take this question. Kistler supports our customers at every phase of the equipment lifecycle, starting at project offset with consulting, engineering test, and application support. During startup with commissioning, on-site support, training, and instruction. Then we offer periodically on-site calibration service, as well with in equipment modification, repair, and spare parts.
Great, thanks for that. And it looks like we're going to wrap things up right there. So guys, thanks so much for taking the time to be with us today and also taking the time to answer some questions. And of course, thanks to all of our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. Lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.